Dear students, today let us we study about the S block elements. So the S block elements are present extreme left in the periodic table, and it comprises the two groups, that is group 1 and group 2. Group 1 of the S block consists of the elements lithium, sodium, potassium, rubidium, cesium and francium. They are collectively known as alkali metals because their corresponding hydroxides are alkaline in nature. That means they are soapy to touch. The general electronic configuration of alkali metals is NS1. Group 2 of the S block consists of the elements beryllium, magnesium, calcium, strontium, barium and radium. These are collectively known as alkaline earth metals because their corresponding oxides and hydroxides are alkaline in nature, that is soapy to touch. The general and they are all found in the earth crust. The general electronic configuration of alkaline earth metals is NS2. Now coming to the general characteristics of alkali and alkaline earth metals. Coming to the atomic and ionic radii. Alkali metals have largest atomic and ionic radii in their corresponding periods. Atomic and ionic radii of alkaline earth metals are smaller than those of the corresponding alkali metals in the same period. This is due to the increased nuclear charge that we know as we move from left to right in a period of the periodic table. Atomic and ionic sizes decreases due to increase in nuclear charge. Atomic and ionic radii of both alkali and alkaline earth metals increases down the group because of increase in the size of the atom, which decreases the effective nuclear charge. Coming to the another property, ionization potential. The ionization enthalpy of alkali metals is lowest in their corresponding periods because of high atomic size, low nuclear charge and very well screened outermost electron, or in other words, it is also called screening effect. The first ionization enthalpy of alkaline earth metals are higher than those of the corresponding alkali metals, while the second ionization enthalpies are lower than those of the corresponding alkali metals. The ionization enthalpies of both alkali and alkaline earth metals decreases down the group. Coming to the another property known as hydration enthalpy. Alkali metals have the atomic and ionic sizes increases down the group. That means lithium ion has least atomic size and cesium ion has highest atomic size. Similar situation also we come across in alkaline earth metals. Lithium ion has maximum degree of hydration, hence its salts are hydrated. The rate of hydration decreases down the group. That's why we get lithium chloride dihydrate, but whereas the other alkali halides do not form any hydrates. The hydration enthalpies of alkaline earth metals ions are larger than those of alkali metal ions. Thus, the compounds of alkaline earth metals are more extensively hydrated. The example magnesium chloride hexahydrate and calcium chloride hexahydrate. They take 6 water molecules as water of hydration. Coming to the physical properties of alkali metals. Alkali metals are silvery white, soft and light, low density, low melting and boiling point. They have weak metallic bonding due to the presence of only one electron in the valence shell. They impart characteristic color to the flame. The alkaline earth metals are silvery white, lustrous and relatively soft but harder than the alkali metals. They have higher melting and boiling point than alkali metals. The lower members impart color to the flame due to the low ionization enthalpy. They have higher electrical and thermal conductivity compared to alkali metals. Now coming to the chemical properties of these alkali and alkaline earth metals. The alkali metals are highly reactive as compared to alkaline earth metals due to their large size and low ionization enthalpy. So, reactivity towards air and water. Lithium reacts with oxygen of the air and forms lithium oxide, that is Li2O, whereas the sodium reacts with oxygen of the air to form sodium peroxide, that is Na2O2. The higher alkali metals reacts with oxygen to form superoxides having the formula MO2, where M is potassium, rubidium and cesium. Because of their high reactivity with air and water, they are normally kept in kerosene oil. With water, they liberate hydrogen gas. That is, the metal reacts with the water to form metal ion and hydroxide ion, and hydrogen is liberated. The reactivity of lithium is less due to small size and high hydration energy than the other metals. Beryllium and magnesium are kinetically inert to oxygen and water due to the formation of an oxide coating on their surface. Similar to beryllium, magnesium burns in air to give magnesium oxide and magnesium nitride. However, calcium, strontium and barium are attacked by air to form only their oxides. They react with water to give their hydroxides and hydrogen. Coming to the reactivity towards halogens and hydrogen. Alkali and alkaline earth metals react with hydrogen to form their halogen to form their corresponding halides, and with hydrogen they form hydroxides with the liberation of hydrogen. Reducing nature. The alkali metals are strong reducing agents than the alkaline earth metals because they undergo oxidation readily. Oxidation means removal of electrons. Coming to the another property, that is diagonal relationship. Lithium and beryllium, the first elements of group 1 and 2, exhibit same properties, some properties which are different from those of the other members of the respective group. In these anomalous properties, they resemble the second element of the following group. Thus, lithium shows similarity to magnesium and beryllium shows similarity to aluminium in many of their properties. This type of diagonal similarity is commonly referred to as diagonal relationship in the periodic table. The diagonal relationship is due to the similarity in ionic sizes and charge to radius ratio of the elements. This charge to radius ratio of the elements is also called polarization of ions. And the diagonal relationship is also due to difference in electronegativities. The cause of diagonal relationship can be explained on the basis of concept of polarization of ions as follows. On moving from left to right in a period, the positive charge on the cation increases and ionic size decreases. Both these factors increase the polarizing power of the cations in a period. However, on moving down a group, the positive charge on the cations remains the same, but the size of the cation increases. This decreases the polarizing power of the cations. On moving diagonally in the periodic table, these two effects partly cancel each other so that similarity in properties occurs. The cause of diagonal relationship can also be explained on the basis of electronegativity as follows. Electronegativity increases from left to right in a period and decreases on descending a group. Thus, beryllium is more electronegative than lithium and magnesium is slightly less electronegative than beryllium. Here I have shown the values. Electronegativity of beryllium is 1.5, lithium is 1. Therefore, the electronegativity of beryllium is greater than lithium. Electronegativity of beryllium is 1.5, magnesium is 1.2. This shows that the electronegativity of beryllium is greater than magnesium, but it is the less than lithium, but it is greater than lithium or almost similar to the magnesium. Since lithium and magnesium electronegativity difference is slightly less or almost nearly equal, these two elements show similar properties. This is about the diagonal relationship. Coming to the anomalous properties of lithium. Lithium differs in many properties from the other alkali metals due to the small atomic size, greatest polarizing power, and highest electronegativity and ionization energy as compared to other alkali metals. All salts of alkali metals are ionic, whereas lithium salts are covalent. Lithium salts are soluble in non-polar solvents while other are soluble in polar solvent, that is water. Lithium is much harder and lighter than the other alkali metals. Lithium is least reactive metal of all the alkali metals. Lithium alone reacts with nitrogen and silicon to form the corresponding nitride, that is Li3N, and silicide, that is Li6Si2. When lithium burns in air, it gives only the monoxide, that is Li2O, while other alkali metals forms peroxides and superoxides. Lithium, when heated in ammonia, forms imide, that is Li2NH, while other alkali metals form amides, that is MnH2. Lithium salts alone undergo hydrolysis and results hydrated salts. Due to the electropositive character of lithium, its various salts are less stable and therefore decompose to give oxides. That's why the lithium carbonate, when it is heated, gives a lithium oxide and carbon dioxide. Lithium nitrate, when it is heated, gives lithium oxide, nitrogen dioxide and oxygen. Whereas the other compounds of the alkali metals, they do not undergo such decomposition. Some of the salts of lithium, like lithium carbonate, lithium phosphate and lithium fluoride, are insoluble in water, while the corresponding salts of other alkali metals are soluble in water. So these are some of the anomalous properties of what? Lithium. Similarly, the many more anomalous properties are there. We have given the important ones. Now coming to the anomalous behavior of beryllium. Beryllium is the first element of the group 2. Differs from rest of alkaline earth metals due to its small size, high polarizing power and high electronegativity as compared to other metals in the group. Beryllium is the hardest of all the elements of its group. The melting and boiling point of beryllium are the highest. It has a tendency to form covalent compounds. It does not react with water even at high temperature. Other alkaline earth metals decompose water, liberating hydrogen gas. So the magnesium combines with water to form magnesium oxide and hydrogen. Beryllium does not react with hydrogen directly to form its hydride. However, its hydride can be prepared indirectly. The rest of the alkaline earth metals combine with hydrogen to form hydrides readily. The hydrides of beryllium and magnesium are covalent in nature, whereas the other hydrides are ionic. Beryllium reacts with alkalis to form hydrogen. Beryllium Be plus 2NaOH gives Na2BeO2. It is called sodium berylate and gives hydrogen. Other alkaline metals do not react with alkalis. That's why we call beryllium is amphoteric in nature. The oxides and hydroxides of beryllium are amphoteric, that is, dissolve both in acids and alkalis to form the salts. Beryllium oxide BeO plus H2SO4 gives rise to beryllium sulfate and water. The oxides and hydroxides of other alkaline earth metals are basic in nature. Beryllium nitride is volatile, while the nitrides of other alkaline earth metals are non-volatile. Beryllium ion, on account of its small size, forms stable complex compounds like BeF3 minus, BeF4 2 minus, etc., while other alkaline earth metals do not form complexes of this type. Now coming to the complex formation tendency of S-block elements. Alkali metals have a weak tendency to form complex compounds. This is due to the lack of inner low energy vacant orbitals and also having low charge on the cation, that is either +1 or +2, which results larger electrostatic attraction between the central ion and the ligands. Of course, the beryllium ion, on account of its small size, forms many stable complex compounds like trifluoroberylate ion, tetrafluoroberylate ion, and so on. However, magnesium ions of the other alkaline earth metals form very few complex compounds. Of course, we don't come across the complexation in alkali metals. The formed complexes of the magnesium and beryllium are tetrahedral in nature. Now, let us compare this property with the p block elements. The small size and the more charge of the elements of the p block make them to form complexes as compared to the s block elements. This tendency to form complex diminishes down the group as the size of the atoms increases down the group. Beryllium fluoride forms a complex halide of the type tetrafluoroberylate, in which beryllium atom has a coordination number 4. It cannot extend its coordination number 4 to 6 due to the non-availability of the d orbitals. So this is the periodic table showing the S block elements, P block elements, D block elements, and F block elements. S block elements are present extremely left to the periodic table. This slide shows about the whatever we have discussed so far about the properties of S block elements. So they have given the S block elements, their properties. They are alkali metals, react with water to form alkaline solution. Alkali comes from the Arabic word alkil, meaning is ashes of the saltware plants. Easily lose valence electrons. Always they form cation with +1 charge. Easily cut with a knife. Found combined with other elements in nature. They are the good conductors of heat and electricity. So here also we have shown this slide the characteristic properties of S block elements. So here there are other properties they have given. They have metallic character, they have low electronegativity, they form basic oxides and hydroxides, and ionic bond with fixed coordination state, oxidation state, and they form characteristic flame colors, and they have a weak tendency to form complex. So this is also a slide showing some of the general characteristics of S block elements. This is a slide showing a diagonal relationship of lithium with magnesium, beryllium with aluminium. The main points of similarities are both have almost similar electronegativities, that is a lithium and magnesium, and both lithium and magnesium are quite hard, and they are harder and lighter than the other elements in their respective groups. Both lithium hydroxide and magnesium hydroxide are weak bases. Both form ionic nitrides when heated in atmosphere of nitrogen. Here also the slide shows about the diagonal relationship of lithium with magnesium. Some of the properties related to diagonal relationship is given. Both lithium and magnesium are harder and have higher melting points. Due to covalent nature, chlorides of both lithium and magnesium are deliquescent and soluble in alcohol and pyridine. Deliquescent means they absorb water. Fluorides, phosphates of lithium and magnesium are sparingly soluble in water. Carbonates of lithium and magnesium decompose on heating and liberate carbon dioxide. Hydroxides and nitrates of both lithium and magnesium decompose on heating to give oxides. Hydroxides of both lithium and magnesium are weak alkali. Both lithium and magnesium combine directly with nitrogen to give nitrites, that is Li3N and Mg3N2. This is the slide once again shows anomalous behaviors of the lithium as we have already discussed. So this is also the anomalous behavior of the beryllium. Beryllium forms the covalent compounds whereas the other elements forms ionic compounds. Beryllium is having high melting and boiling point. The other elements of group 2, they have low melting and boiling point. So beryllium does not react with water even at elevated temperature, but the other members, they react with water. Beryllium does not combine directly with hydrogen, but other elements, they combine directly with hydrogen to form the corresponding hydrides. Beryllium does not combine directly with halogens but whereas the other elements, they combine with halogens to forms the halides. The halide of beryllium is covalent. Halides of the other elements of second group, they're all electrovalent. So this slide also shows about the anomalous properties of the second group elements. This slide shows about the weak tendency to form the complex. Complex formation is a common feature of the D block elements. But however, this you don't find in S block elements. S block metal ions have no low energy vacant orbital available for bonding with lone pairs of surrounding ligands. Therefore, they rarely form complexes. So here also the same thing is shown. The weak tendency to form complexes is due to the lone pair of electrons of the ligands can donate to the central D block metal ion and to form the dative covalent bonds. Dear students, go through these aspects and try to learn about the properties of S block elements. Thank you.